The integrated circuit, which we use to build logic circuits, is one of the most important inventions of the 20th century. We can use hardware description languages to describe complex logic circuits. Both these descriptions are in the Verilog hardware description language. On the left-hand side, we have a 2-input multiplexer. It selects between two inputs 1 and 2 based upon another input select. The multiplexer's output is I1 if select is false, and I2 if select is true. On the right-hand side, we have a 4-input multiplexer. This selects between 4 input signals. That requires 2 select signals. We can generalize the logic of the 2-input multiplexer to create the 4-input multiplexer. We can use Boolean logic to perform binary arithmetic. A sum is computed on 2 inputs A and B and a carry in. This generates 2 outputs. The sum is the exclusive OR of A, B, and the carry in. Cout is true when at least 2 of the inputs are 1. It's also true when all 3 of the inputs are 1. A 1-bit adder that generates a sum and a carry is known as a full adder. We can string together full adders to create n-bit adders. In this case, we've built a 2-bit adder out of 2 full adders. Here's a wafer of silicon. This is a slice out of a very large single crystal silicon. It's 300 millimeters in diameter. Semiconductor manufacturing plants perform an array of sophisticated manufacturing steps in order to create integrated circuits on this wafer. The wafer is cut up into chips. To understand how digital logic works, we need to review some circuit basics. The voltage across a resistor is proportional to the current through the resistor and its resistance. The current through a capacitor depends on the capacitance and also on the rate of change of the voltage across the capacitor. This is a cross-section of a MOSFET, a metal oxide semiconductor field effect transistor. This is the basic building block of digital circuits. We have a source and a drain that are connected by a channel. The channel sometimes conducts and it sometimes does not conduct current. Whether it conducts is controlled by a gate structure. The gate is separated from the channel by a thin layer of glass or silicon dioxide. Now keep in mind that we use the term gate both for this structure in a MOSFET and also for logic gates, but those are 2 different types of gates. When we turn on the transistor, current can flow between the source and the drain of the transistor. Complementary metal oxide semiconductor circuits, or CMOS circuits, use 2 types of transistors, an N-type and a P-type. The N-type transistor conducts between its source and its drain when the gate voltage is above a certain value. The P-type transistor conducts between source and drain at negative gate voltages. The complementary nature of the action of the gate helps us build efficient circuits. This is a circuit for a CMOS inverter. Logically, the output is the Boolean inverse of the input. When the inverter input is low, the pull-up is on. When the inverter input is low, the pull-up transistor, the P-type, is on. That connects the output to the positive side of the power supply. When the input to the inverter is high, the N-type pull-down is on. That connects the output to the ground or low side of the power supply. In steady state, only one of the transistors on the inverter is on at any given time. We can think about the operation of the inverter as CMOS switches. We model each of the transistor as a switch. The pull-down switch is turned on when the input signal to the gate is high. The pull-up is turned on when the signal to the gate is low. Logic gates are electrical circuits that produce continuous signals. They don't produce clean logic zeros and ones. Instead, they produce voltages and currents that vary over time. The circuits operate in a range of voltages between ground and the plus power supply terminals. These signals change over time, and they move between three different ranges. Lower voltages we define as a logic 0. Upper voltages we define as a logic 1. The range in between we define as an unknown logic value, or X. In order to get between logic 1 and logic 0, the signal has to go through the X region, but we want to minimize the amount of time that the signal stays as X. This transfer curve shows the relationship between input and output voltages on the inverter. The basic shape of the transfer curve shows that at low input voltages, the output voltage is high. It very rapidly translates to a low output value. Only a very small range of input voltages put the output in this X or unknown range. Noise margin is the difference between the worst case input signal and the worst case output signal. Good noise margin means that even a mediocre output from one gate will be treated properly by the next gate. We have two noise margins, one for low, the other for high. As we saw a minute ago, we can model MOSFETs as voltage-controlled switches. The gate of the MOSFET has a parasitic capacitance that we need to take into account in order to understand the delay incurred through a logic gate. The transistor's channel can be modeled as a resistance that needs to be taken into account during delay calculations. This simple example shows how a value propagates through a chain of inverters. The 0 input to the first inverter turns on the pull-up transistor, which charges the parasitic capacitance at the input to the second inverter. That high value at the second inverter turns on the pull-down, which discharges the parasitic capacitance at the third inverter. The parasitic resistance and capacitance in logic gates means that it takes time for a logic gate to change its output. We can measure the delay through a logic gate from one input voltage to another. A typical pair of values to compare is the 10% voltage and the 90% voltage. We can measure the rise time, or the amount of time it takes for a logic gate to rise to a logic 1. We can also measure the fall time, the time it takes for the output to fall to a logic 0. In many cases, a logic gate's rise time and fall time are different. That's because P-type transistors are not as efficient as N-type transistors. The voltage waveforms that determine both rise and fall time have an exponential form. We refer to the product of the resistance and the capacitance in the circuit as its time constant. The response of the circuit is proportional to the time constant. Wires also have delay because realistic wires have resistance and capacitance, and in some cases inductance. If we think about a wire as a string of RC segments, the delay through that wire is proportional to the square of the number of segments, or the square of the length of the circuit. Complex logic circuits have many paths through them. In this case, the single output has two different paths, above and below. The ultimate delay through the circuit could be determined either by path 1 or by path 2. On the left-hand side, we see an example of fan-out. The NOR gate feeds two different NAND gates. It has a fan-out of 2. The circuit on the right has 4 possible paths. Any one of these circuits might determine the worst case delay through the entire logic circuit. Logic gates burn energy as they operate. A very simple case for understanding energy consumption is an inverter that transitions from a 0 to a 1 to a 0. The amount of energy consumed in the sequence of transitions is CV squared, where C is the capacitance of the logic gate. Notice that this energy consumption doesn't depend upon the resistance of the transistors. Yield is a measure of how many actual working circuits we get out of manufacturing. That is, of all the chips on a wafer, how many of them actually work. Circuits may also fail over time as they operate. A common characteristic for failure rate as a function of time is what's known as a bathtub curve. The failure rate for chips in the first few hours of their operation is very high. This is known as infant mortality. After the initial failure rates, the failure rate usually goes down to a very low level, usually for a matter of years. At some time, though, circuits start to fail. This is known as aging. Given the significant voltages and currents that these circuits operating on and the extremely small size of the transistors, it's not surprising that chips would eventually fail due to aging. Logic designs and integrated circuits can be designed to a number of different requirements. The cost of the product, which includes both the design cost and the manufacturing cost. Battery life, the degree of programmability. We can trade off, in many cases, characteristics of the circuit to improve one of the characteristics, perhaps at the expense of a different characteristic. I/O devices connected to logic may be digital or analog. Interfacing refers to circuit design that connects an I/O device to a main logic or computer device. A very common circuit in interfacing is the voltage divider. We have two resistors connected from power to ground. The voltage across each resistor depends on the ratio of that resistance to the total resistance from power to ground. Here's an interesting example of a circuit, an LED. When the LED is on, it has a relatively small voltage across it, usually around 0.7 volts. We connect a resistor to the LED to supply current. We can create a programmable LED by connecting this circuit to a logical output. When we set the output high, it turns on the LED. When we set the output low, it turns the LED off. Thanks for watching.